would like you to pause the video and try these three problems, writing the null and alternative hypotheses, because this is really important practice for when we're doing an actual hypothesis test. So in the first problem, we have a governor is concerned about their negatives, the percentage of state residents who express disapproval of their job performance. Their political committee pays for a series of TV ads, hoping that they can keep the negatives below 30%. They will use follow-up polling to assess the ad's effectiveness. So my claim there is that the percentage of people that think negatively of the governor is going to be 0.30 or 30%. So that's what the null says it's going to be. It's status quo. But the alternative is they're hoping that these ads can keep the negatives below 30%. So the alternative would say that P is less than 0.30. Is a coin fair? So a coin is either fair or it's not, right? It's not higher or lower. So my alternative would say that the proportion of head or flips that would give you tails or heads would have to be 0.5, right? 50%. And the alternative would just say, if it's not fair, then it's not 50%. And in the last one, only about 20% of people who try to quit smoking succeed. Sellers of a motivational tape claim that listening to the recorded messages can help people quit. So here we know that the null hypothesis is P equals 0.20 because that's the percentage of people who try to quit smoking that actually are successful. And then if they're listening to a motivational tape, we would expect more people to quit after hearing the tape. So the alternative here is P is going to be greater than 0.20. So how can we provide evidence to refute the null? By using what probability theory tells us about the behavior of a random variable sample proportion, p hat, we know that it's centered at p and it has a spread of the square root of p times 1 minus p over n. For large enough sample sizes, n, its shape is approximately normal. Our strategy will be to determine if the observed value, p hat, is just too unlikely to have occurred if the null were true. If the probability of such an outcome is too small, then we'll reject the null in favor of the alternative. Okay, that probability value is called the p-value, and we're going to look at that more in depth here. So recall our first problem about the group of 371 Valencia College students where 42 were left-handed. If I pose the question, is this significantly lower than the proportion of all Americans who are left-handed, which is 0.12, I'm looking to see if there's strong evidence to suggest the proportion of all Americans who are left-handed is lower than 0.12. So to do this, we need to perform a hypothesis test. And this test is specifically called a one proportion z-test because there's one proportion I'm looking at. I'm looking at the proportion of left-handed students. So first we need to write the null and alternative hypotheses. So here, the null, if you remember from doing this before, is p equals 0.12. The null says the proportion of all students that are left-handed is going to be 0.12. The alternative, on the other hand, thinks it's lower because it says, is there strong evidence to suggest the proportion of all Americans who are left-handed is lower than 0.12? So there's my null and there's my alternative, which we discussed in the previous video. Now, to decide if the proportion of all Americans who are left-handed is lower than 0.12, what probability do we actually need to determine? Well, there's a few things we need to find here. We need to find p hat, which in this case would be the number of students in the sample, which was 42 out of 371 that are left-handed. And for that, if we divide 42 by 371, we get 0.113. We need to find the standard error of p hat. Okay, so for this one, we're going to go back to the square root of p times q over n. And P here is 0.12. That's my claim. Times 1 minus 0.12. And then divided by my sample size. And when you calculate that, you get 0.017. So I'm going to use that to figure out where p hat goes on the normal model. So I need to find z. How many standard deviations away is my sample proportion p hat? So remember, that's going to be your value, p hat, minus the mean, divided by the standard error. And when you divide those, you get negative 0.41. So now, what probability am I determining? The probability that z is going to be less than negative 0.41. This alternative inequality should always match up with your probability. So that's what we're going to be finding. Okay, so picture the normal model now. We know that the mean, which is your population proportion of 0.12, goes in the middle. And then you can add 0.017 to each of the values starting with 0.12 and then subtract. So if I add 0.017, you get the following numbers. And then if I take 0.12 and subtract 0.017 and keep doing that, you get these following numbers. So where is p hat exactly? Well, I know 0.113 is in between 0.103 and 0.12, and it's negative 0.41 standard deviations below. So not quite a half a standard deviation below. So that's where my z is. And I know that I'm looking for where z is less than that. So that would mean I'm going to shade to the left. So I'm finding the area to the left of the flag. So to do that, I'm going to find the probability that z is less than negative 0.41. And to do that, I need to use either a table or technology. I'm going to use technology. I'm going to look for normal CDF. My lower bound here is negative 100. My upper bound is my flag in this case, so negative 0.41. My mean is 0. My standard deviation is 1. So if you go into the calculator, remember you're just going to go to second vars, and we're picking number 2. And we have our negative 100 for our lower bound, comma. Our upper bound is negative 0.41. The mean is 0, and the standard deviation is 1. And then hit enter, and we get 0.34. So that's the probability, right? In other words, there's a probability of about 34% that the proportion of all Americans is less than 12% that are left-handed. Okay, so in the last example, we determined that the probability that our observed statistic occurred, given the proportion of all Americans is 0.12, is 0.34 or 34%. That number right there is known as the p-value. Okay, the p-value of a test about a proportion p is the probability computed assuming that the null is true, that the test statistic, which is p hat, would take a value at least as extreme, so that means as high or as low or as different as the one observed. The smaller the p-value, the stronger the evidence against the null. So here what we're basically saying is if the null were true, if the percentage of left-hand individuals is actually 12%, there's a 34% chance I would find a statistic that's that low as the one I observed. So a 34% chance means, that's a pretty strong enough p-value statistic to say that the null is probably, we're going to go in favor of the null. So at this point, you have two options. You're either going to reject the null hypothesis, and we do that when the p-value is small, which again, we'll talk about like how you know whether it's small or large. And then you could fail to reject the null or do not reject the null. And we do this when the p-value is not sufficiently small. Again, we'll talk about that, okay? What you never do is you never accept the null. So don't ever say, I accept the null, or say the null is true. All we can say is that either we are rejecting the null in favor of the alternative, or we are not rejecting the null. And we always refer back to the alternative. Think of it as like when you go to court and, a defendant is found not guilty, right? That's different than being found innocent. A defendant's never found innocent. They're found not guilty. We just don't have enough evidence to find them guilty. So it's very much the same thing, okay? So should we reject the null or fail to reject the null hypothesis for the previous example? What do you all think? Well, 34% actually is strong enough and large enough, a p-value, that we would fail to reject, okay? So what we would basically say here is we're failing to reject the null. Okay, and we'll talk more about like how we know whether to reject or fail to reject. If we're failing to reject the null, it means we're siding with the null. So there is not strong evidence to suggest what. So we always respond in place of the. We always refer back to the alternative. So there's not strong evidence to suggest, what did the alternative say? Well, the alternative was that the proportion of all Americans that are left-handed is less than 12%. So we don't have enough evidence to suggest that. There's not strong evidence to suggest the proportion of all Americans who are left-handed is less than 12%. Okay, please pause the video and you can try this problem on your own. So in order to use the normal model, which we did in the previous example, you need to check your conditions. Remember, those are the independence assumption, which we check by doing randomization and the 10% rule. And then also you're checking the sample size assumption, which we check by looking at the success failure. So you want to show that each of those were satisfied in our last example. So in the last example, if we go back and look at randomization, it does say that a group of 371 Valencia College students, it doesn't say that they were random. So we need to ask ourselves, are those 371 students representative of all students? And we would go with yes. That's a large enough sample to say that there's, a variety of different students that could represent the population, because ultimately we want our sample to do a good job of representing the population. So for random, yes, it is checked. It is satisfied. 371 students are representative of all Valencia College students. Next, I need to check, and let me fix that. Next, I need to check my, independence assumption, right? So random kind of covers that, and so does 10%. So why don't we check the 10% condition next? Remember, your sample can never be more than 10% of the population. So 371 is not more than 10% of all Valencia College students. Those two conditions take care of the independence assumption. So that tells us that the each subject or each person in the sample is independent. The last condition I need to check goes along with the sample size, right? So I need to check the success failure condition, which remember just says that n times p has to be greater than or equal to 10, and n times q, which is just 1 minus p, also has to be greater than or equal to 10. So here n, my sample size is 371, and I'm going to multiply that by p, and p is just 0.12. And we know 12% of 371 is way more than 10. It's actually 44.52. And then 371 times 1 minus 0.12, or 0.88, is also greater than or equal to 10. And that gives us 326.48. So since all those conditions are satisfied, we can use the normal model to represent our distribution. And that is the end for this video. Please join me in the next video where we'll continue to do more hypothesis testing.